Hi there. We talked today in class about cross-sections. What we are doing with our cross-sections here, which is the third lesson of our Unit 6, what we're doing with cross-sections is we're calculating the volume of a 3D shape. And we do that by essentially graphing the base of the shape. And so what I mean by that is when you look at your boundaries, when you look at what you're going to draw here in a bit, what you're seeing there isn't the shape itself, but is the bottom of, say, like a box. Imagine a box here, and you have the bottom of the box that would like sit on a table, right? That bottom of the box is what we're going to be looking at. Okay, and so we're going to be graphing that base, and then growing out of that base, you have to imagine this 3D shape. Again, kind of think of a box growing out of what you've drawn. And with that 3D shape, we're going to be slicing it up into particular cross sections, right? And so that's what this little visual here is showing. We have our region here. This is the base of our box. And then here you have to kind of visualize these little triangles as poking up out of the box, right? And so we're going to be cutting these triangles and we're going to be calculating their area. Or it might not be a triangle, it might be a square or a rectangle or a semicircle, but we're going to be calculating the area of that, and we're going to be putting that area into our integral in order to figure out what our volume is. Okay, so kind of that's what cross sections are in a nutshell here. I've provided your 2D formulas that you need to know: squares, triangles, equilateral triangles, semicircles, and rectangles. Most of these you should have seen before. Equilateral triangle may be the one that's probably the most unfamiliar for many of you. The only one that you need to make sure you're careful about in terms of our work, and we're going to demonstrate one of those in example 2, is semicircle. Semicircle has one additional thought here because of this R. In a semicircle we have our radius, which means we need to do one thing to our segment in order to actually calculate the area, or sorry, to calculate the radius. Like I said, we'll get to that. Okay, so here's what we're going to do. We have example 1. We're going to start with our step 1, which is to graph the given functions. Okay, so we have y equals x squared plus 1. We have y equals 1. We have x equals 2. And x equals 0, which is the y-axis. So our 4 functions here. And so the region bounded by those 4 functions is this little triangular-ish looking piece. Okay? So your instructions will be very straightforward. They'll say find the volume using cross sections. Right? And then they'll tell you which cross section to use. In this particular case, we are going to be using equilateral triangles. And not only will they tell you what what shape to use, they're even going to tell you which way we are oriented, right? In this particular case, we're going to be oriented towards the x-axis. And so our little segment's going to be drawn in perpendicular to the x-axis, just like our big R's and little r's have been drawn in 6.2. We're going to be drawing our little representative segment perpendicular to the x-axis. Our numbers are going to be x numbers. Our equations are going to be x equations, right? So everything's in terms of x here. So again, nothing's really hidden. The part that you are mainly responsible for with these cross sections, or I should say largely responsible for, are your area formulas. You do need to know your 2D formulas, right? And so in this particular case, since we're doing equilateral triangles, we do need to know that the area of an equilateral triangle is root 3 over 4 s squared. And then again, we know this is dx because they tell us we're perpendicular to the x-axis. Okay, so x bounds, my x bounds, since we're talking x's, we're looking left, right for my bounds instead of up, down. Up, down would be y bounds. My left bound here is 0. My right bound is 2. Right, leftmost x, rightmost x. And then your equation here, they're always going to give you a spot for your upper minus your lower. Our upper minus your lower is going to go right in here. And so I'm going to go ahead and draw in my little segment here, my representative segment, just like we did with area. This is going to be perpendicular to the x-axis. Okay, here's the x-axis, we're perpendicular to it. My upper is called x squared plus 1, and I'm going to leave it as x squared plus 1 because we are going to be in terms of x. Okay? And my lower is called 1, so we have upper minus lower. So we're going to go ahead and solve this one by hand. Let's clean it up first. We have 0 to 2, root 3 over 4. 1 minus 1 is 0. So we have x squared squared, which is x to the 4th. At that point, we can apply power rule. This root 3 over 4 is just a coefficient, so it's just going to hang out. And we're going to add 1 to that exponent and divide by the new exponent. Okay, and then we're going to plug in our upper minus plug in our lower. Our upper here, when we plug in 2, we get 32 over 5. And I'm going to go ahead and combine this 4 times 5 to make it 20. And then minus my lower, plug in that 0, we're going to get 0 over 5, which is just 0. And then you could potentially reduce this. 4 comes out of both of them, and this would make 8 root 3 over 5. Okay. Let's go ahead and look at another here. Example 2. Our boundaries are y equals root x, y equals 0, and x equals 4. Okay, so this particular cross section is the one that you do want to make sure you're a little bit more careful about. It's one of the formulas you're going to have to manipulate a little bit here. Okay, we have semicircles. Okay, let's go ahead and start with drawing our shape here. We have y equals root x, y equals 0, and x equals 4. Okay, and so there's my region. Okay, and so in this one we have semicircles, and they are perpendicular to the x-axis. So let's go ahead and draw in our representative segment. Okay, so semicircles is 1/2 pi r squared, and then we know this is dx because we're perpendicular to the x-axis. Since we're x-oriented, my x-axis bounds here, I should say my left and rightmost points here, are going to be 0 to 4. Okay, and then my r still does have the upper minus lower. My upper in this case is root x, and I'm going to leave it as root x because I'm in terms of x. And my lower is 0. But here's the tricky part, or I should say the important part about semicircles. The thing you have to remember is, take a moment here, picture the semicircle, right? Remember, this is the base of some sort of box, and coming out of the top here are a bunch of semicircles, right, that we're cutting out here. So it's kind of creating a little dome-ish looking shape. Well, picture the semicircle coming up off this page, coming over, and retouching down. All right, I'm going to go ahead and see if I can draw it kind of sort of a little bit here. Right, that's our little semicircle. It's coming out off the page on one side, over and down. Well, my upper minus my lower here, I can't just put upper minus lower into the radius because that's not a radius. Look at that semicircle. My upper minus my lower is the diameter, right? And so to find the radius, I would need to take that diameter and divide it by 2. Okay, so from here on out, we're just going to solve it like we normally would. We have 0 to 4, 1/2 pi. Root x minus 0 is just root x, so we have root x over 2. And root x over 2 squared is x over 4. Okay. And then I'm going to clean this up one step further, and I'm actually going to pull this 1/4 over to the 1/2 and make that 1/8. Because at that point, it's just power rule. We're going to add 1 to the exponent of x, so making it x squared, divide by that new exponent. Then we're going to plug in our upper. 4 squared is 16, divided by 2 is 8. And minus, plug in your lower, you have 0 squared divided by 2, which is 0. Anything times 0 is still 0. And so this is 1/8 and 1/8 cancel, and we get pi. Okay, we're going to look at two more here. Example 3, we have our graph, x squared plus y squared equals 9. For those of you who recognize it, this is a circle formula. This is a circle with radius 3. And so if you recognize that, fantastic. You can go ahead and graph it. For those who maybe don't recognize it, you would need to potentially graph this one so you could see it. And so you'd take a moment and you'd solve for y. Okay, so I'm going to go ahead and do this off to the side here. I'm going to rewrite that x squared plus y squared equals 9. And I'm going to solve for y so that I can graph it. Let's go ahead and subtract the x squared over. And we'll square root both sides. Remember, if you take a square root, it has to be plus or minus. And so that's what you'd graph then. In your y1, you'd graph positive 9 minus x squared. In your y2, you'd graph negative root 9 minus x squared. Let's go ahead and show that. In y1, we graphed positive root 9 minus x squared. In y2, we're going to go ahead and graph negative root 9 minus x squared. And you'll see here it'll graph a circle. Now mine is probably going to be a little bit stretched out simply because of my window. You can still see the circle. There it is. Okay. So that would be if you didn't recognize the circle formula, you would have that available. Okay. After that, we're back to where we have been. We've got our graph. We're going to go ahead and sketch in our region, or shade in our region here. Okay. And then we're looking, we have cross-section. We are doing rectangles. So already I'm thinking, okay, what's the area formula for rectangle? Base times height. They tell me my height is 2. So now I know it's base times 2. For my rectangle formula. Let's go ahead and put that in. My base is going to be my upper minus my lower times my height. And then they tell us we are now oriented towards the y-axis, right? We're perpendicular to the y-axis. And so now, just like what we did in 6.2, everything's going to be in terms of y. Y bounds, y equations, that type of thing. Okay? So, let's go ahead and draw on our segment so that we are perpendicular to the y-axis, just like we've been doing with our big R and little r when we've been revolving around the y-axis. Okay, and so then our bounds here, now we're talking y bounds, so we're concerned with uppers and lowers. Right, my lower in this case is -3. My highest bound is 3. And then over here for our base of our rectangle, we have upper minus lower. My upper function minus my lower function. Now because we are oriented towards the y-axis, I do need to take this equation and I need to turn it into an equation that only has y's within it. Right, so I'm going to go ahead and go over here. X squared plus y squared equals 9. I'm just rewriting it. And I'm now going to manipulate this algebraically until everything is with the y. The whole equation is in terms of y. Right now the equation is in terms of both x and y. Okay, so let's go ahead and subtract this y squared over. Okay. And then square root both sides. Remember, if you square root something, it's plus or minus. The plus is for the positive side of the graph, the minus is for the negative side of the function. Right. Positive side of the function, negative side of the function. Okay, so over here on our graph now, we're going to name our upper. Our upper is the positive side of that function. So we have root 9 minus y squared minus our lower, which is the negative side of that function, negative root 9 minus y squared. Okay. And then you could solve that by hand, or you could, actually this one might be a little bit difficult to solve by hand. This one in my mind would be a calculated problem anyway, which is what I was about to say. We're going to make this one a calculated problem so I can demonstrate that technique again for those who are still having some questions with it, having some trouble with it. Okay, so in the 89, you will be doing F3, which says calculus. And right here on number 2, it says integrate. Okay. To integrate, you're going to go ahead and type in your function. We have the square root of 9 minus y squared. I'm going to go ahead and make this plus, minus a negative is plus. Square root of 9 minus y squared. And this is times 2. dy, so you put comma y for the dy, and then comma your lower bound, which is negative 3, and then comma your upper bound, which is 3. And when you hit enter, get your approximately 56.548. Okay. In your 84, you would hit math, 9. 9 is f and int, and you'll get this little integral sign. And you'll do negative 3. Oops, sorry about that. Let's start over. Okay, negative 3 to 3. And then we have our root 9 minus y squared. And then again, I'm going to call this minus a negative a plus. Root 9 minus y squared. Times 2. And then dy. And you get, once it finishes calculating, well, I'll put it back underneath once it finishes calculating, but that's how it would calculate. Oh, there we go, 56.548. And so you've confirmed you've done it correctly. Okay. Okay, so we are on to example 4 here. Example 4, which is the last one we're going to do. We have our boundaries, 2x minus 2 and x squared minus 2. So I'm going to go ahead and take a moment. We're going to graph this. And again, we're going to make this another calculator 1, just like we did with in example 3. That way we've done 2 by hand, 2 in our calculator. We're practicing it both ways. Okay, so we have x squared minus 2, which is a quadratic, shifted down 2. And we have our line here of x squared, or sorry, 2x minus 2, which is a line at the y-intercept being negative 2 and a slope of 2. And I'll be honest, my sketch probably isn't quite on. We'll graph it here in a bit anyway so that you can see what it should technically be. But again, the sketch is just to kind of give us a rough idea. Okay, so our formula here, we are told our cross sections are going to be squares, so we're already thinking that that's side squared, right? Base times height of a square. And we are perpendicular to the y-axis, so we know everything's in terms of y, our bounds, our upper minus our lower. Okay? And we're going to go ahead and draw in our representative segment here so that it is, in fact, perpendicular to the y-axis. Okay, so bounds first. I'm going to go ahead and take a moment here and review how to calculate an intersection for those who need that review. So all I've done here is graphed the two functions. Okay, while this is graphing, I'm going to input it into my 84 as well. Okay. Oh, my little sketch was pretty close, actually. Okay. Okay, so to find intersections, on 89, you're going to hit F5. You're going to come down here to intersection. And it's going to ask you first curve, second curve. So you're going to say yep for the first curve, yep for the second curve. It's going to ask you for a lower bound and an upper bound. Okay, so I'm going to go ahead and calculate this intersection first, my upper intersection. Lower bound and upper bound, and they give me the point 2, 2 as my intersection. Now you want to be careful. With this particular function, it doesn't matter too much, right? Because look, at your x and your y happen to be the same thing. Okay, but if you were looking at an intersection where the x and y did change, you do want to make sure you're using your y, right? We are y oriented here. Okay, so I'm going to go ahead and use that 2 then. Okay, It's going to be my upper, right? Because that's the highest point right here. The highest point in my shaded region. We're talking y bound, so highest and lowest. My lowest point is over here. I'll go ahead and demonstrate this one on the 84. 84, you do second calc. Intersect is down here. First curve, second curve. And 84 is they actually just ask you for a guess. So you're going to go ahead and guess, yeah, sure, that looks like it's about right. And this one, take a look, your intersection is different between the two variables, right? And so you want to make sure you're using the correct one. Again, we are y-oriented, so we're going to use the -2 for this one. Okay, that's going to be my lower bound here, because that's the lowest point, the lowest y value of my shaded region. Okay, so I have my bounds. You also, just as a reminder, could find it by hand by setting these two equations equal to each other. You'd end up getting, taking all of one side, subtracting it over, getting it equal to 0. Just like we've done in 6.1 and 6.2, you could then factor or do quadratic formula. Okay. So now we're on to our upper minus our lower. Our upper is this quadratic, y equals x squared minus 2, but I can't put in x squared minus 2 because I have to be in terms of y. So let's go ahead and alter this. We're going to add 2 over to the other side. And then square root both sides. Remember, if you take a square root, it's plus or minus. Okay? And so this side of the quadratic is the positive. So this is root y plus 2. Okay, minus my lower. My lower is the 2x minus 2. But again, I can't call it 2x minus 2. I have to be in terms of y. I'm y-oriented. So I'm going to go ahead and change this. Let's add 2 over to the other side. Y plus 2 equals 2x. And then divide 2 over. And you get y plus 2 over 2 equals x. Okay, and so that's what I'm going to be putting into my lower. Y plus 2 over 2. Okay. We're now going to take this, we're going to plug it in. Okay. Again, you can plug it in on either calculator. I'm going to go ahead, you know what, I was going to do it on the 84, but 84s are pretty simple. Remember, one more time, you're just going to hit math, and then it's number 9 down here, f and int. It'll generate your integral for you. I'm pretty sure you can take it from there. You're just filling it in. Let's go ahead and demonstrate it one more time on the 89. Okay, so 89 we have, you're going to hit F3 for calculus. Okay, and then it's number 2, integrate. We're going to type in our function here. Square root of y plus 2 minus y plus 2 over 2, and that's squared. We do comma y for dy, comma our lower bound, comma our upper bound. When you calculate that, it generates 0.533. Okay. And those are cross sections.